As you see in the last video that uh, stochastic gradient descent about when we are training the neural network with mini batches. So mini batch is what we are going to do. We are going to divide the whole data set into small batches, so small data sets. So when we are, training the neural network on that, what happens now? All the training steps. That means like the backpropagation algorithm and the gradient descent algorithm and the weight adjustment. Those things will happen only for a batch, not for every single data instant, but it happens for a batch. So we are not going to do it for each and every data. So we are going to apply a batch, and per batch we are going to do the weight adjustment. So that's what the stochastic gradient descent about. So you can see the video, the previous video, it explain it well. And also other than that, I will post the uh, we links to the videos of that uh, three blue one brown channel. We have like lots of good animations on deep learning and neural networks, so you can watch these and concrete the idea about neural networks and their algorithms running behind. Okay, so now I will move on to activation function. So under this we will talk about two main types of activation functions, uh, linear activation and non-linear activation. So later I will explain what happens, what's the usage of activation function, and what the purpose of having an activation function in a layer. Okay, so first, now you know that activation function is like what we are going to do. Each neuron, we are going to take some input from the previous layer, and those will be multiplied with the corresponding weight, and at the neuron, the bias will be added. So then we are going to calculate Z. So Z will be basically sigma Wx plus B. And that Z will be applied through activation function called F, and the output of the neuron will be calculated, and that output will be passed through the preceding layer by multiplying them with the corresponding weights of the nets. And so other thing is that activation function, like we have defined activation function for each layer, not for each neuron. That means like, okay, so let's say the hidden layer one, we are going to define one activation. So that will be the activation function for all the neurons in that layer, right? So we can't have different activation functions uh, in the same layer for different neurons, but you can have different activation functions for different layers, but not for the neurons in the same layer, right? So when you are going to define activation function, that will be defined for the neurons, all the neurons in that layer. So we are going to define activation function for a layer, right? Okay, so basically we have two main types: linear activation and nonlinear activation. So in linear activation, we will first talk about linear activation, and later we will move to nonlinear activations. So linear activation is quite simple. Now you can see we are going to calculate the Z value as I mentioned earlier. Then the Y, that means the output of the neuron, will be the same Z, right? So Y equals Z. So that's what you call the linear activation. So you can see Y equals Z in the sense now Y value can range from like uh, you can see now minus infinity to plus infinity. So what will happen, like let's say, okay, the Z value is plus 2, right? So the Y value will be also plus 2, right? And if the Z value is minus 4, let's say, right, the Y value will be again minus 4, right? So Y equal Z. So that's what you call the linear activation, right? So now I will explain what the purpose of having activation function later, but now keep this idea in your mind. Okay, so then we will move on to the second type of activation functions, uh, nonlinear activation functions. Under this, we are going to find like sigmoid, tanh, Relu, Leaky Relu, softmax. These are not the only activation functions we are going to find under nonlinear activation functions. We have more, and some activation functions are not mentioned here, but they are also there. So, but we will discuss the main types. So these five will be discussed here, but keep that in mind. We have like several other activation functions, like adapted activation functions from these things, right? Uh, so first one will be the sigmoid activation, or we refer this as the logistic activation, where we are going to get Z from sigma Wi xi plus b, and the Z will be applied to the equation shown here, 1 over 1 plus E minus Z. So this will be applied here. The Z will be applied here, and the Y will be calculated from there, right? So the specialty about this thing, so you can see the Z value can be ranged from minus infinity to plus infinity. So it can be any value, any real number between minus infinity and plus infinity. But the specialty here that Y will be uh, like restricted between 0 and 1. So y is ranging from 0 and 1 no matter what the z value, right? That means the output of this, if you are having like a sigmoid activation function for a layer, all the neurons in that layer can only output a value between 0 and 1 regardless of the z value, right? So you can simply verify this equation, right? So let's say now when the z value is, let's say, right, so z value is minus infinity, that means the smallest value that we can have, let's say, right? So then what will happen, uh, so this will be basically 1 over 1 plus E minus infinity, sorry, minus minus, you can see there's a minus sign, so that will be plus infinity, and basically this will be like E plus, sorry, E infinity is infinity, so it's like infinity plus 1 will be infinity again. So this will be 0, all right? So the lower boundary of the y value will be 0. Now when z is positive infinity, what's going to happen? That this will be like will be something like this, minus infinity, and we can write it like 1 over 1 plus 1 over plus infinity, which will give us 1 over 1 plus 1 over infinity, and this will be basically 1 over 1 plus 0. So this will result on 1. So you can see now this is saturated between 1 and 0, right? Yes, so that's what you call the sigmoid activation. So this is a non-linear activation. So I will explain about this linear and non-linear activation functions and what are the usages later. But I will first go through the activation functions, and they are like a different type of activation functions. Okay, so then we have the activation function called tanh, or we call this hyperbolic tangent. Uh, so this is the same kind of like sigmoid, but the only difference is that this has a range between the y has range between minus 1 and plus 1, right? So that's the specialty, that the sigmoid ranges from 0 to 1, but this ranges from minus 1 to 1, and the output will be, so the again if you have a layer between tanh activation, all the neurons will give you output in between minus 1 and plus 1 regardless of the z value, as I mentioned earlier. And then the other type, the most so the sigmoid and tanh, so these are like suffering from something called vanishing gradient, the vanishing gradient problem, right? The vanishing gradient problem, this and also the sigmoid as well, right? So I will explain what the vanishing gradient problem in coming weeks, but not today. So keep that thing in mind. There is some issue with these activation functions, but they are used in neural networks, but they have some issue called the vanishing gradient problem, the activation function. If you are like having the activation function, the tanh or the sigmoid activation function, they are suffering from the vanishing gradient problem. Okay, so now, yeah, so the Relu activation function is basically the commonly and the mostly used, the most famous activation function. So you can see ReLU is used everywhere in all the all the neural networks. ReLU is a mostly and commonly used activation function in the world, and this is quite similar. So this is actually uh, like a very simple activation. The thing here that if the z value is greater than 0, right? If the z value is greater than 0, uh, that the y value will be, right? Y will be z. So you can see, right? Y will be z. So whatever the z value will be there for the y as z. But when the z is less than 0, right? So if the z is less than 0, in that case, the yeah, so the activation function, uh, like yeah, give y equal 0, right? So y will be equals to 0 in that case, right? Okay, so this is what you call the ReLU activation function. So ReLU is one of the most commonly used activation functions. So this kills the z values less than 0, and the y will be 0 in that case, right? So the ReLU is one of the commonly used activation function. And the next type is Leaky Relu. I mean, in Relu, the rectified linear unit, we have some other adapted version as well. So Leaky Relu is one of them, and we have like P Relu, the parameterized Relu, and Relu exponential linear unit. Likewise, we have several modified versions of Relu, but I'm not going to discuss about everything. So for example, now Relu is used in self-driving cars by NVIDIA. Self-driving car, they have used Relu. So they have like different applications. We can't exactly say this is the best activation function for to use, but we can't say it like that. Most of the activation functions are application dependent. I will explain these things after discussing about the activation functions. So basically in Leaky Relu, what's going to happen? Now here, if the y z is greater than 0, what's going to happen? The y will be z. Simply y will be z, right? So this is something that we already know. Y will be z. But if z is less than 0, now you can see if the z is less than 0, what's going to happen? Y will not be z, but it will be like something like this, a z. So let's say like 0.2 z, right? So what will happen? Let's say z is like 5, right? So it's a z, let's say z is like 5. So what's going to happen? I mean, yeah, yeah, sorry, let's say z is 5 minus 5. So y will be here. That means y will be minus 5 into 0.2, which will give you 0.1, right? 0.1. So it will be 0.1, right? Uh, is it? Yes. Okay, so that's what the leaky relu is about now. I mean, it's not going to cut off the values. I mean, it's not going to make y value 0 when z is greater than, sorry, less than 0, right? But it will like have a value, but with a small gradient, right? So y equal a is z, where like y equals 0.2 is likewise. Understood? Okay, so then we will move on quickly to the softmax activation. Now, softmax is uh, actually quite similar to the sigmoid activation function just we discussed earlier. There's only one difference, right? I will show you the, yeah, now, yeah. So let's assume that, okay, so you can remember the iris flower example, right? Or, yes, let's say the iris flower example. Now in iris flower example, what you can get, uh, yes, so what you can get is like 3 neurons at the output layer, right? So this is something that you already know. Now this is due to like we have 3 labels in the set of for iris flower example: setosa, virginica, and versicolor. Okay, so 3 neurons. Now let's assume that we are going to uh, assign soft sigmoid activation here. Let's say sigmoid, right? Sigmoid activation. Now then you can see that like we can have now this is the neuron for setosa. I'm talking about the last layer, virginica and the versicolor, right? Uh, yes. So this is what you like. We can see at the last layer of the setosa. I mean, if you are going to develop a neural network for the iris flower example. Now, if you have a sigmoid activation, what you can do, I mean, what happens actually in the sigmoid activation, if you have the sigmoid activation at the last layer, you are going to probably get values between like 0 and 1. So we can get values like this, right? Like this. So I mean, these are values in between 0 and 1, right? 0 and 1. So what's going to happen, like softmax is quite similar to sigmoid, only one difference that if you have instead of softmax, sorry, instead of sigmoid, if you had like a softmax activation here, what you are going to get, not 0.8, but it will be like 0.8 divided by 0.8 plus 0.4 plus 0.1. And here also 0.4 divided by 0.8 plus 0.4 plus 0.1. And here also 0.1 divided by 0.8 plus 0.4 plus 0.1. Now it's like, I mean, you are going to get some value here, right? Yeah. So what will be the value? So it will be like 1.3 divided by, sorry, 0.8 divided by 1.3, right? And the other one is like 0.4 divided by this one. 1.3, and also the last one 0.1 divided by 1.3, right? So that's what you are going to get as the output. Now the specialty here that I will show you this thing, that we are going to get a probability. Actually, we are going to get a probability here. Yes. So let me get the values, the actual answers for these things. 0.8 divided by 1.3. Yes. So it's like, yeah. So here it will be 0.63 and yeah, 0.62 actually. 0.62. This should be 0.62, and the other one will be like 0.4 divided by 1.3. So it will be like 31, 0.31, and lastly we have 0.1 divided by, sorry, yeah, 0.1 divided by 0.1 divided by 1.3, right? So you are going to like get a value in between, yeah, 0. Yeah, it will be 0.07, right? 0.07. Now the specialty about this thing is this is going to add up to 1, right? So that means in a softmax layer, you are going to get the value I mean, for the last layer, or let's say one of the layers, you are going to get a probability. So softmax is commonly used in uh, softmax is commonly used in at the for the last layer of classification problems. So that's actually the application of softmax. We are going to definitely, most of the times we are going to use softmax activation in the last layer of classification problems. So what's the specialty about this? I mean, you can use the sigmoid as well, but here it says now, if you are looking at the sigmoid activation, so 0.8, now we can say the prediction. So let's say this is the last layer. මේක අපි කියමු last layer එක. Last layer එකේ 0.8ක් එනවා සෙටෝසා වලට. 0.4ක් එනවා වර්ජිනිකා වලට 0.1. So අපි මේකෙදි කියන්නේ prediction එක සෙටෝසා කියලා. We are going to say like the prediction is setosa since it's the highest value. I'm talking about the last layer of a neural network, right? So in the softmax layer, what we are going like, we are going to get a probability. So we can say like 62% it says setosa, 31% it say like virginica, 7% it says versicolor, right? So we can have a probability, right? So last layer or the output layer of classification problems, we are going to use softmax layer. So other thing is that we discuss about these regression problems, right? I mean yeah, I will show you that as well. Now we discuss about this thing, the linear activation, right? So linear activation is commonly there in output layers of regression problems. Now let's say the self-driving car, we are going to predict the steering angle. So the output layer, there will be one neuron. Most of the regression problems, if you are dealing with regression problem and you are building up a neural network for regression problems, the last layer probably it will be like one neuron there, since we have like one value to predict, right? So let's say the steering angle, the risk of having heart disease, or the stock price tomorrow. Likewise, we have some values. Now, my point is that in regression problems, the last layer, there will be most of the time, I'm not talking about like all the times, but most of the time there will be one neuron. There are some instances we can have multiple outputs as well. But in regression problems, most of the time the last layer will be like one neuron will be there, right? So my point that neuron should have a value range. Like let's say if you are predicting the steering angle, so it will be like minus 360 to plus 365. Two rotations are there, right? Two full rotations in the steering wheel. But actually in the self-driving car, they are not predicting the steering angle. It's like a steering signal, something like 1 over the turning radius. I will talk about that later. But let's assume we are going to like get the steering angle. So it will be like the output layer. I mean, the output neuron should give a value in between minus 360 and plus 360. So we have to have a linear activation. Now it's not between 0 and 1, right? So keep that thing in mind. So regression problems, most of the times the output layer, they are going to assign a linear activation function as the activation function. And for classification problems, we will use softmax or sigmoid, but it's better to use softmax since we are like getting a prediction like out of 1 or out of 100. So it can be easily, we can give the prediction. Now we can say like 62% setosa, right? Likewise. So for example, what we can do, like, okay, so let's say that we have designed a neural network for image classification, where we are going to like input, let's say we are going to input image, right? A image, and there will be a neural network, right? A neural network will be there, let's say, convolutional type neural network, right? And this neural network is going to predict, let's say, three things. Okay, whether this is a cat, dog, or a rabbit. So we have defined a neural network, or we have built up a neural network which gives us like the which can identify when the image is given. It can identify whether this image contains a cat, dog, or a rabbit, right? So we are going to like, let's say we are going to right right, we are going to input some image, right? And this image is going to predict whether this is a cat, dog, or rabbit. So what's the advantage of having a softmax here is that it's going to give it like this 0 0.9, 0 0.6, sorry, 0 0.6, 0 0.04, right? So it's going to like give us a probability. So we can say like, okay, it says 90%, this is a cat. So I mean, don't think or don't expect that you are going to get some values like this. I mean, you are not going to you are not going to get like values like this frequently. Some of the times you may get, right? Like this for the output layer. No, not 100, but it will be like something like this 0.9999, and this will be like 0.000001, and this will be like 0000, right? Likewise, we are not going to get 100 always, but a value like 0.98, 0.9, 0. Likewise, right? So that will be always a probability. So softmax will be used in activation for the last layer of classification problems most of the times, but you can use it some other places as well, right? So that's the last activation function that we discussed under the nonlinear activation function. Now, I know that you have lots of questions here that what is the, I mean, that's the theory or what's the base behind using these activation functions, depending on what we are going to use activation function. Okay, depending on what we are going to use softmax, depending on what we are going to use sigmoid, depending on what we are going to use softmax, I mean Relu or Leaky Relu. So what's the theory behind? So what kind of applications we are using this, what kind of application we are using this? So you have to have a clear idea on you, right? So there's nothing like that, right? So we can't say, okay, this is the activation function for stock market prediction, this is the activation function that you should use for this kind of application, this is the activation function that you need to use for this kind of application. No, you can't say it like that. The thing is now, actually what you have to do, uh, most of the times now we have tested results from past researchers. We can say, okay, now as I mentioned earlier, in the self-driving car, they are using this elu instead of relu activation, elu activation. Now what you know the relu activation, right? So we discussed about the relu activations previously. So let me go back to uh, uh, the the note, and here now you know what the relu activation, right? So the relu activation is something like this, right? So this is, sorry, uh, let me draw it like this, right? So this is what you know the relu activation, right? So the relu, yes. So the relu activation will be something like this, right? So I mean, we have like several applications now by practice. So make a කරලා බලලා මේක මේ application use trial and error, right? කරලා බලලා අපිට කියන්න පුළුවන් හරි. For this application, the softmax is good. For this application, the tanh is good. For this application, sigmoid is good. For this application, for this kind of a task, relu is good. But other than that, there is no theory behind, right? Okay, so this is the activation function to be used. No, not like that. No theory, no factors to be considered. So this is like mostly trial and error. What you have to do, like we have to change the activation function. We have like several tools, like so we can change uh, the number of layers, number of hidden layers, the neurons in hidden layers. We can change the activation functions. We can change the optimizers, right? So we can do lots of things, right? But I mean, right? So we have to like do it by ourselves. Now, you know that we can build up infinite number of neural networks for a single application, right? So the task is to find the optimal, or first task is to find the best, right? But what's the task of activation function? I will quickly go through that thing, right? So now you know that having a neural network, right? Having a neural network is going to what we are trying to do. Let's say we have a neural network like this. I mean, I will not going to draw the neural network, but assume that there is a neural network, some kind of a neural network, and we are going to like have some inputs here and have some outputs here, right? Some outputs here. So let's say that okay, uh, like we are going to, right, for our simple problem, well, let's say that we are going to take our simple problem, right? So the temperature and the humidity and rain, no rain, right? So the temperature, like let's say x1, x2, y1 and y2, right? So I mentioned this in the first week as well. So in a neural network, what we are going to do, like we are going to build up an approximator, right? So we are going to approximate some kind of a thing like this, y equal fx, right? So here y is represented by y1 and y2 and x is represented by x1 and x2. Keep that thing in mind. So we are going like approximate y as a function of x. So that's the task of a neural network. So x can be an image, y can be a number, anything, right? So it's going to somehow now, when we are going to give an image, the image will be x and the output will be whether it's a cat, dog, or rabbit, right? So we are going to classify it. Now, actually what we are doing in a neural network, we are approximating a function, right? We are approximating a function. Y, we are going to approximate is using x, right? So now, what the purpose of this f? I mean, if you are using this f, right? So we have like this is the f is the function approximate by the neural network, right? So actually now we can say this y can be something like this, right? A1 x y, let's say y1, A1 x1, A2 x2, right? Right? And yeah, A1 x1, A2 x2, and we can say A0, the constant, right? So if you have this kind of a thing, you definitely know that this will be a line, right? So this will be a line, y1, and let me draw it with 1, x1. So this will be a line. So this is a linear function, right? So this is a linear function. So this is to be a linear function, right? So right, but sometimes the relationship between x and y will not be linear, right? Will not be linear, right? Now let's say, okay, so we are going to give an image, so the features will be each pixel, right? So features will be each pixel. So we are going to like somehow map these pixels into the steering angle, right? So in that case, that's not simple, right? So your function, now let's say, okay, now in a advanced case, okay, now we are going to build up a neural network like this. Let's say a CNN and y to be steering angle, right? And we are going to input an image, right? We are going to input an image of the road, right? Now you know the features will be each pixel, right? Right? So x will be like pixels. So we have like, let's say in the original one, it's used like 200 into 66, the size, right? 200 into 66. I'm talking about the NVIDIA self-driving car, right? So that's what they are. That's what the input is, right? So it's going to give an input. Now, let's say this is one feature, right? Feature one. So let's say x1. So what's the relationship between y and x, right? So we can't say, right? We can't say exactly, but it not necessary and it won't be a linear thing, right? X1 and y, it will be something like this, right? Now, I mean, I will show this, show you this. Uh, yes, right? Uh, Now, this will be, I mean, okay. So steering angle, let's say 360. This, let's say minus 360. And let's say this is 0, right? This is 0. And let me take it here. Okay. Now this function, I don't know the pixel value. This pixel value, let's say I'm going to take a consider a single pixel, and with that, it might have some relationship like this. We don't know, right? I can't exactly say, right? So this value will be ranged from 0 to 255. Since pixels can like, if you use a grayscale image, the pixel value will be ranged from 0 to 255. Now, when the pixel value range from 0 to 255, this value, like, I mean, the steering value might change like this. So this is not a linear function like this, right? So this is a non-linear function, right? Non-linear function. So in order, like, if you know your problem, the relationship between your features and labels, relationship between your x and y. So if you know that that's a non-linear relationship, definitely you have to use non-linear activation functions. Why? What's the reason? Now, I mean, if you are going to do it like this, let's say you have your sigmoid activation, right, in a single layer, what will happen? In a single layer, you will definitely get y equal this term, you will definitely get, right? 1 over 1 plus e minus z. So this is not like y equal mx. This is a nonlinear relationship, right? So you can remember this is nonlinear, right? This is a nonlinear relationship, not like that. I mean, uh, this had something like this, non-linear, but this is linear, right? So non-linear relationship, that means, okay, so if you are, that means what's going to happen? Let's say that you have several layers and you are using non-linear activation functions. That's saying what? Your x will be mapped to y using non-linear equation. So definitely your function will be, the mapping function y to, sorry, x to y will be definitely a non-linear, having an nonlinear relationship, right? So we know that, I mean, the pixel value will not be like having a linear relationship between y. It will definitely have a nonlinear relationship, right? So keep that thing in mind. So if your problem needs a nonlinear, if you know that this is nonlinear, this won't be like linear, right? Pixel value එක වැඩි වෙන්න steering angle එක වැඩි වෙනවා. එක pixel එකක් වැඩි වෙන්න steering angle එක අඩු වෙනවා. අපිට එහෙම කියන්න බෑ. pixel value එකත් එක්ක මේ වගේ relationship එකක් තියෙන්න ඕනේ. මේක වැඩි වෙද්දි මෙහෙම වෙන්න පුළුවන්, අඩු වෙද්දි මෙහෙම වෙන්න. We can't exactly say. So that kind of thing, we have to map x to y using nonlinear activation, right? So that's where you are going to use nonlinear activations. So if you are using nonlinear activations, I mean, we can't exactly say that, okay, for this self-driving cars use this, for stock market prediction use this, but in previous research, what they have done is like they have gone through these things again and again. They have like empirically obtained, empirical in the sense like they are not going, not by theory, but doing is like trial and error method, right? Empirically. So we have like to obtain. So some of the research they are suggesting that, they are recommending that, okay, so self-driving car, as I mentioned, use Elu, not Relu. So we can see now natural language translation. I can remember like they are using tanh activation. So that kind of special things are there. But other than, we have like for our neural network, we have like we have several tools, and out of those activation functions, we have to find the best, right? So that's the method of doing that. Otherwise, like there's no theory that, okay, use this for this application, use this activation for this activation. Not like that. But if you know that it's nonlinear relationship between y and x, definitely you have to use nonlinear activation functions, as I mentioned. Now you know what are the nonlinear activation and what are the linear activations, and keep that thing in mind. Regression problems, most of the time for the output layer, we are going to use linear activation. Classification type problems, we are using like sigmoid and softmax for the output layer, and uh, but it's easy to use softmax rather than sigmoid for the activation function for the classification problem at the output layer. Okay, so that's it about the activation functions quickly. And yeah, so then we had to discuss about the, yes, then we have discussed about the loss functions, right? So when you are like discussing about loss functions, the most important thing is that we have two main types of loss functions. So the loss function is the function that going to calculate when the neural network is going to predict a value, and like it's going to take the actual value and get the error. So that's what you call the loss function. The error calculating function is the loss function. So two main things regarding the loss functions. If you are using like this is for a regression problem, you have to use the mean squared error, and for classification problems, you have like use cross entropy loss. Now the other thing is that the loss functions, uh, like these are the fundamental type loss functions like mean squared error and the cross entropy for regression and classification respectively. But other than that, we have like some adapted and modified loss functions as well, like mean absolute error and R2 score. And for cross entropy loss, we have like categorical cross entropy, binary cross entropy, right? We have several cross entropy functions, like, but these are the two fundamental type of loss functions available for this thing. And some of the time we are using cosine proximity in language modeling, like natural language translation. We have like a specific uh, loss type called cosine proximity. Likewise, we have several other, but these are the two fundamental type: mean squared error and the cross entropy. Right. So if you like, okay, if I simply explain what's mean squared error, right? So in mean squared error, this is what we are going to get. Mean squared error. This is a mean MSE, right? So okay, so this layer is the output layer. Sorry. Yeah. So let's say that this is the output layer, and if your predicted value yp, let's say yp is 10.5 and y actual is let's say 5. So this is a regression problem, and your loss or the error will be 10.5 minus 5 square, right? And the mean, now here one neuron is there, so the mean will be 1, right? So if you have 2 neurons, you have divided by 2, and you have to add the other loss as well, right? So that's what you call the mean squared error simply. And the cross entropy loss is bit different, right? In cross entropy loss, let's say if you have like 2 neurons and the classification type problem, right? So assume that we are using like the softmax activation at the last layer, right? So then y will yp and ya. So you know that this will be like 0.8 and this will be 0.2. Since we have like add them up, then it should be 1, and this will be like 1 and 0. So the cross entropy loss will be simply, I will get the equation here, the cross entropy quickly. So this is the equation for the cross entropy loss. Okay, right. So the cross entropy loss, and yes, so it says like you can see now 1 over n is basically, now we have 2 neurons here, so it will be 1 over 2, and y actual is 1, and y predicted is log 0.8, and 1 minus 1 y actual. So y actual is 1, so 1 minus 1, and predicted will be 1 minus the predicted is 0.8. 8, right? Sorry, so this should be like, I will write it here, 1 minus 0.8. So let me like get everything to shift a bit. Yeah, and I'm here. Okay. Yes. So yeah. So here now, then the second one will be like basically it will be, yes. So then the second neuron we have to consider this one. So first thing is written for this one, and I will use a different color, let's say. Okay, so I'm talking about now this neuron, and the actual value is like 0, and the predicted value will be is 0.2, and 1 minus actual is 0, and log predicted 1 minus predicted. So predicted is 0.2, right? So it will be 1 minus 0.2. So that's how, yes. So that's how you are going to calculate the uh, yeah. So that's how you are going to calculate the uh, the uh, the cross entropy loss. Right. So that's how you are going to calculate the cross entropy loss. So mean squared error and the cross entropy. So depending on the problem type, that means depending on whether it's a classification or a regression problem. Right. Understood? Yes. Good. So now, yeah. So that's it about the loss functions, and we will quickly move on to the remaining part. Yeah. So we talked about the gradient descent algorithm. So the gradient descent algorithm is the algorithm that's going to adjust the weights and biases in order to minimize the loss, right? So we know that we have to talk about the gradient. So this gradient is given to us, right? So as I mentioned, now this term is given by the backpropagation algorithm, which we are going to discuss on this Tuesday. The next Tuesday, we will discuss about the backpropagation algorithm before going into the practical session, right? So we will discuss about the backpropagation algorithm, right? And so we know about the, yeah. Okay, now we know like we gone through the like the gradient descent algorithm, right? So what happens in the gradient descent algorithm, and now we have to talk about the learning rate. So learning rate is actually this component. So you can see this is the component that we are talking about, the learning rate. Now depending on learning rate, we have like uh, discuss several things, right? So now what is going to happen in the learning rate? So this learning rate should be like fixed by us, right? In most of the cases. So what's going to happen now? You can see, okay. So here now, okay. So let's assume that initially the weight is here, right? The error and the weight one and the error, right? So what's going to happen now? Okay, so the weight adjustment, now you know, it's like weight minus eta daba e over daba w, right? Okay, now this is the weight adjustment, right? So the gradient. Now what's going to happen if the gradient, oh, now let's say this is a large value, let's say like 10, right? So what's going to happen? Like, so the weight adjustment will be multiplied by 10. So what's going to happen now? Let's say the gradient here will be negative gradient, right? So the negative gradient, so we are asked to like add the weight. Now, since the weight adjustment is multiplied by 10, what's going to happen? Now, this weight from here, like, so like, let's say if this is 1, right? If this is 1, now it will be changed to somewhere here, assume, right? But when it's 10, what's going to happen? Now 10 times larger weight adjustment will be happens. So it will be like gone somewhere here, right? So then what's going to happen, right? So then it's going to happen like, okay, so now the gradient is negative. Sorry, the positive gradient is there now, right? The gradient is positive. Now it's like, okay, asked to like uh, reduce the weight, right? And again, since it's going to multiply by 10, it will go there and go here, right? So likewise, it's not going to reach the minimum, right? So it's going to like go away from reaching the global optimum loss, right? So it not will be converged. So converge in the sense. So this is what you call convergence. Now, if the loss, if the weight, right? So this is what you call the convergence. Now, if right, so if the, I mean, if the weight can reach the value which gives the minimum loss, right? So that's what you call the convergence, right? So this is not going to be converged, right? This is not going to be converged here. You can see at this point will not be reached. And what we can do, right? Other than that, okay, so without making like the learning rate too large, what we can do, we can have like okay, a small value, a very small value, right? A very small value, like let's say, okay, 0 point, right? Uh, right? So let's say like 0.001. I mean, more less than, let's say, less than that, might be less than that, right? So what's going to happen now? Okay, so here, now let's say let's assume that the eta is 1. So what's going to happen, like let's say, okay, from here it asks us to go here originally. එක කියලා හිතුවොත් එහෙම මේක ඊටා ලර්නින් රේට් එක කියලා හිතුවොත් මේ වගේ ගානක් යන්න කියන්නේ. හැබැයි 0.01ක් වුණොත් මොකද වෙන්නේ? ඒ වුණොත් එහෙම අර යන්න කියපරත් වඩා අඩු ගානක් තමයි යන්නේ. ඒතර වෙන්නේ මේ හරියට යන්නේ. Right? So, I mean, this is definitely this is going to reach this point. It's obvious, right? Since it's like very small steps, so definitely it's going to reach the convergence point or the minimum loss. But the issue is that this is going to take too much time, right? So time is the issue here, right? So in that case, what you have to do, like not big, not too much big, not too much small, right? So we have to have a proper learning rate, right? Proper learning rate. So we have like somehow adjust the learning rate accordingly. Now, in the usual case, what's going to happen, like what's going to happen is that we are going to, I mean, yes, so we are going to right? In the usual case, that the thing is, like the learning rate should be started at a big value, and eventually we had like reduced the value of the learning rate, right? So the thing is, now you can see, now we are like we are trying to come to a I mean bottom of a hill, right? So in that case, so in the initial time, so we can take big steps, right? Big steps. But when you are like eventually coming down to the bottom, we like to take careful steps. So the learning rate should be started at the big value, and eventually we had like reduce the learning rate. So that's the method of changing the learning rate, right? So that's how we are going to change the learning rate. So start at a big value and eventually change the learning rate. So I mean, we need to like take careful steps when you are like coming to the like I mean later epochs යන වැඩි වෙන්න අපි learning rate එක අඩු කරන්න ඕනේ. මුල් epochs වලදී ලොකු learning rate එකක් තියලා පොඩ learning rate එක අඩු කරන්න. මොකද epochs ගාන වැඩි වෙනවා කියන්නේ අපි පොඩ පල්ලෙහාට එනවා කියලා මෙන්න මේ error එකේ. Right? Understood. Okay, so the other thing is that now this is a good thing where good instant where you can analyze the learning rate. Now these things we are going to see when we are going like we are going to implement practically, when you are going to implement the neural networks practically, you are going to see this kind of graph, right? So this graph is drawn like the loss versus epochs. So what's going to happen, like this is where we are going to increase the number of epochs and we are going to measure the loss, right? So what you can see here, now if you have in this case, the case number one, right? So if you have like big learning rate, when you're like increasing the number of epochs, the learning, the error is going to increase, right? Like this. So you can see the loss will be increased. I mean, you are going to see these graphs. I will show you in this Tuesday, right? So these graphs can be drawn and visualized. So this is where we are going to understand. Okay, so this is where you are going to identify. Okay, this is the error with the loss. Our learning rate is too high, or our learning rate is too small, right? So that kind of things can be analyzed by looking at these graphs, by analyzing these graphs. So these things are quite important, right? So that's why I'm taking this amount of time at the initial stage of the course. But when you're like moving forward, we are not going to take that much time for this theory since I mean, this is the most fundamental thing. These things should you these things are the things that you should keep in your mind, right? So these are the fundamental things. This makes your foundation. So this is quite important, this analyzing these things, right? So I mean, you can see these things when you are like training a neural network. So that's why I'm discussing these things. Okay, so then what happens, the learning rate is too small, right? It's going to like minimize its loss, right? So you can see loss like Arduino, but can you see now, let's say in this epoch, right? Let's say this is epoch 100. So what happened, the loss here is greater than the loss here. So that means, okay, so this is going to somehow converge, right? But it takes time. But before that, if you have a good learning rate, an intermediate value, it's going to reach the optimal loss before uh, uh, before this curve, right? So we can see that here, right? And another important thing that I have to show, that this takes time, right? Other than that, uh, so this one, I mean the green color one, high learning rate. So high learning rate is something like this. I will use this graph, right? So you can see now, if the learning rate is high, sometimes this can happen, right? Okay, so here to here and here to here, here to here and here to here. Right, so it can bounce between two intermediate values. Now what will happen here? The loss is, sorry, the gradient is negative, and it's going to like go here, and then the loss is, sorry, the gradient is positive. So bounce between these points. So that can be happen. So that's illustrated here. You can see, right? I mean, it's converge. I mean, converge means it's somewhere here. මෙන්න මේ point එකේ තියෙන්නේ. මෙන්න මේ point එකේ තමයි මෙයා වෙනස් වෙන්නේ. Not here, not the minimum loss, right? වෙනද? Minimum එකට ගිහලා නැහැ. හැබැයි මැද value එක දෙපැත්තට පැන පැන ඉන්නවා. Right? So that's illustrated here, right? So these kind of things can be visualized when you are training the neural network. So in that case, we can analyze whether this is a problem with the learning rate. You can see these things in coming weeks, right? Okay, so keep that idea about the learning rate. Okay, so then yeah, so then we have discussed about this adaptive optimizers. So adaptive optimizers are like now the fundamental type is the gradient descent algorithm, but we have some adaptive optimizers. So what's the purpose of having adaptive optimizers? So these are modified advanced version of gradient descent algorithm. So these optimizers, like in the gradient descent algorithm, we are not going to change the learning rate. It's done manually, done by us. We have to change them manually. But this adaptive delta, adaptive gradient, and adaptive momentum. So these kind of optimizers, like they are adjusting the learning rate accordingly. Accordingly in the sense now, like, so it's going to analyze the instant, I mean, analyze the situation, analyze where it's currently, right? And uh, right, so it's going to analyze the position, right? If it is here, it's going to adjust the learning rate accordingly. If it's here, adjust the learning rate accordingly. If this is here, adjust the learning rate accordingly. Likewise, it's going, these adaptive optimizers are going to adapt the learning rates and other parameters accordingly according to the situation, right? So that's what the usage of adaptive optimizers. So we are now not currently using the stochastic gradient descent or gradient descent that much. We, this adaptive delta, adaptive gradient are best, and they are well performing than gradient descent. So they can adapt, they can change their parameters, they can adjust their parameters according to situation where is current the current loss, according to the current loss, right? So you can see now, these are like, these should be like huge steps, and eventually these should be like small steps to converge to reach the convergence point, right? So we are using adaptive optimizers rather than gradient descent or stochastic gradient descent, since these adaptive optimizers are, they are going to like adjust their learning rates, adjust their parameters according to the situation, right? Okay, so that's it. So these are like some adaptive optimizers that we have, right? So keep those things in mind. So on Tuesday, we are going to discuss about the backpropagation algorithm. So with that, we can finish the theories of feed-forward neural network. Then we are going to directly move on to the practical implementation. Okay, so we will discuss the backpropagation in detail on Tuesday. Thank you very much.